Hi friends, I am Azad. Welcome to my YouTube channel Ace with Neotech. First of all, I would like to thank you all for viewing my video about binary search. I hope I have taken input from you and improve the same in the following content. Let's go to a new video which is a coding challenge walkthrough session about a Leet Code problem, square root of x. Let's go to the Leet Code website to look at the problem statement. So the problem statement is given a non-negative integer x, compute and return the square root of x. Since the return type is integer, the decimal digits are truncated and only the integer part of the result is returned. So this is the problem statement. What it means is like we not only gonna find perfect squares, but we are also gonna find imperfect squares and truncate the output results to the decimal digits are truncated. For example, if the input is 8, we will output as 2 because the square root of 8 is 2.82842. So we don't want the decimal part, we will truncate it and we will return 2. So this is our problem statement. So let's go on to the slides and discuss how I approach this problem, and then we move on to the coding solution. Okay, let's see how we can solve this problem. We need to find the square root of 6. What we can do? We can use a naive linear approach. Basically what it suggests is that we will fix our base case, like for square root of 0 it will be 0, square root of 1 it will be 1. Then what we will do is like we will loop from number 2 till the given number 16. So first we will fix the result as 1 because the square root of the minimum number less than 2, which is square root of 1, is 1. So we will fix that number in the result. We will start from 2. We will square that number and find whether the square is equivalent to the given number. If it is not, we will check whether the square is less than the given number. Yes, it is. So we will update the result to 2. Okay, then we will move on to the next number 3. We will find the square of 3, which is 9. So 9 is equal to 16? No. 9 is less than 16? Yes. So we will update the result to the start number 3. Next we will go increment the start by 1. So we will check the square 16. Yes, the square of 4, 16 is equal to 16. So what we will do is like we will fix the result as 4 and break from the looping condition. So our result will be 4. So what is the runtime complexity of this solution? It's square root of n. Okay, this will work for very small input. What if we want to find square root of 64? So we need to go through from 2 to 8 in order to find the square root of 64, which is like 7 iteration. So not so much. What if we want to find the square root of 625? So we have to go through from 2 to 25, which is about 24 iterations. Little bit it starts to build up the complexity. Can we do better? Yes, we can, by binary search approach. So here I took the input of 64 in order to better explain. So same case, we will fix the base case for square root of 0 and 1 to 0 and 1 respectively. So instead of looping from 2 to 64, we will fix a condition whether the start, which is 2, is less than or equal to end, which is 64. That's our loop condition. So first we will fix the result as 1. We will start from 2 and end with 64. We will find the midpoint, which is 33, and check the midpoint square, which is 1089. So we will check this value whether it is equal to 64. No. Whether it is less than 64. No. So we don't update the result value here. Then we will use this midpoint and fix the end position to midpoint minus 1, 32. And find the midpoint from 2 to 32, which is 17. Square it, check with this variable. So both are not matching the condition, so we will keep the result as it is. Then we will update the n pointer to mid minus 1. We will keep the start pointer as 2, and we will update the mid pointer to, we will update the end pointer to mid minus 1. So which is 16. So the midpoint between 2 and 16 is 9. The square is 81, which doesn't match our conditions, both conditions. So we will keep the result as 1, and we will keep the start point as 2. We will update the end pointer to mid minus 1. Again find the same. We will we now find the mid square is 25, which is not equal to 64, but it is less than 64. So in this case, what we need to do is, like, we found a square value which is less than the 64. So we will fix our result to the mid value 5. So since this is less than 64, what we can do is, like, we can update the start value to 5 plus 1, which is 6, and we will keep the n value as 8. We will find the midpoint between 6 and 8, which is 7. So the square is 49. Again, it is not equal to 64, but it is less than 64. So in this case, what we will do is, like, we will update the result pointer, result container, to 7. We will keep the, we will update our start position to 7 plus 1, which is 8, and keep the end position as it is. The midpoint is 8, and now we find the square of 8 is 64, which is equal to our target value 64. So this is our result. We will fix our result as 8. Yeah, that's it. We find the result square root of 64, which is 8, and the runtime complexity is logarithmic of n to the base 2. So see here, if we want to find the square root of 64 using linear approach, it will take from 2 to 8, around 7 iterations. But in case of binary search approach, it takes only 6 iterations. Not much improvement, but a little bit improvement. What if we want to find the square root of 625? The binary search algorithm can easily search the square root of 625 in 9 iterations compared to 24 iterations required for linear search. Thereby, this is a scalable algorithm to find the square root of a given number. Okay, let's move on to the implementation in Java as well as Scala. Now we have coded for the Java implementation, which solves the perfect squares. Let's run through some couple of examples for 4 and 64. Okay, we got the perfect squares. So let's run through this solution in the Leet Code. You see here, it accepts for our perfect square. Let's submit the solution. Okay, for imperfect square, our output returns 1. So the expected one is 2. So let's fix that. For solving this, we need to tweak our binary search algorithm to find the square of a perfect square by adding one more container for the intermediate result. For example, if the square if we multiply mid into mid and find the square, which is double equal to x, we will return the result as it is, as a perfect square. What if the square is less than our target x? So we will move our mid index, move our start index to mid plus 1, and at the same time we need to store the intermediate result in the result variable. So this one tweak will solve the imperfect squares problem. So let's run through our solution to find whether our input is correctly producing the output for 8. Yeah, so for 8 the square root is written as 2. So let's run through this solution in Leet Code. Okay, so our solution got accepted for 8, but we failed for a very large input. So the output expected is 46339, but our output is not producing the exact value. So what was the problem? Let's dig deep. Okay, so step 4. Okay, this is a very huge number. When you divide this number by half and multiply that number with itself, it produces a value greater than the integer containers maximum value. So what we have to do is, like, we have to tweak our algorithm to accept very large inputs. Thereby we change our data structure from int to long. So that's the solution for this particular problem. Let's run through that example. Okay, we found the result 46339. So let's paste this sample code in our Leet Code. Okay, we got the success for this submission. That's it with the Java implementation. Let's move on to the Scala one. Okay, let's run through this solution in the Leet Code on Scala. Okay, we have completed the assignment for both Scala and Java. Both of the solutions are available in my GitHub link. Please check, and thanks for your support. Bye.